Hello everyone, this is Jeremias Blendin from Intel. Today we have a P4 workshop talk from Kishan, Brian, and Don with the title Pins Packet I/O. Kishan is an experienced engineer working on software development for networking devices like routers and switches. He is working on P4 programs and the P4 runtime server for Google's SDN infrastructure. Kishan is an active member of the Pins community that helped to open source the P4 developments to Sonic. He has experience in dealing with distributed systems, architectures, and the performance at scale required of such systems. Kishan also worked on the high availability needs for these systems that cannot afford downtime or failure. He also provided technical leadership and front-ended several projects throughout his career. Don has spent the last 25 years working in the telecoms and networking domain in various capacities, from QA automation tester to vice president of network engineering for a global network. Before joining Intel recently, he spent 12 years doing next generation networking research at the AT&T Foundry and the Open Networking Foundation. Brian recently joined Intel after spending nearly a decade working on open source and SDN platforms at the Open Networking Foundation. Brian is involved in a number of open projects at the intersection of the SDN control plane and programmable network hardware, including Pins, Stratum, P4, ONOS, and P4 OVS. And with that, I'll hand it over to you folks, and I'm looking forward to your talk.
Welcome all to the Packet I/O presentation. The presentation will be kind of run over by myself, Kishan, followed by Don, and then later by Brian. So at an overview, these are the topics that we're going to cover. We are going to cover packet in and packet out on the packet I/O. And on packet in, we'll look at providing kind of the status as of today on Sonic, what it provides, what are its capabilities, limitations, and then we'll briefly go over the enhancements we did from Pins side with respect to adding some new metadata and then separating the domains and things like that. And also some of the future enhancements and features that we have in the roadmap for packet in. And packet out will be similar. We'll look at the current Sonic layout, what it provides and its limitations, and then look at some of the enhancements we have, and finally the roadmap. So let's start with the packet I/O, like the packet in format in the Sonic. So Sonic today basically provides the NetDev interfaces for all the front panel ports or the physical ports. So these are Linux NetDev ports, and they are created during the initialization of the Sonic various layers. And the way the packet in works is essentially the switching ASIC receives the packets, and then the kernel module basically puts these packets into the NetDev interfaces for each of these ports. And how exactly they work? It's essentially we have something called the control plane policing in Sonic, and as well as the ACL flows that can be installed by various applications. And once these punt flows are installed, by default, these packets are all sent to the NetDev ports. And the vendor module basically uses the information from the ASIC with respect to which port the packet arrived in, and then it puts in that metadata and uses it in the kernel module to kind of distribute it to the right NetDev socket or to the NetDev port. And the applications essentially open a socket on the NetDev ports, and then they'll be able to receive the packets that come on them. So as you can see, the problem here is that it's essentially a free-for-all, meaning like the packets received by or the packets intended for different applications are received by all applications. And this is essentially a problem in the sense that we don't have a separation of domain. And the way that applications today handle it is they either go with some kernel socket filtering to kind of listen for packets that they are interested in and then drop the rest of them, or they might even use a more application level filtering to kind of filter in the packets that is needed. But as you can see, this is very inefficient. If you're writing application level filtering, then you're pretty much duplicating the work that the ASIC did at the hardware level. So it's not scalable, and this is one of the problems that we felt needs to be addressed in the current model. And another requirement that popped up is essentially having more metadata than just the ingress port on which the packet arrived. For various number of applications, for example, traceroute, like we would be interested in knowing which egress port this packet would have taken if it had gone with the punt or without the punt, what would have been the output port for this packet. And then as well as some of the other important information that got recorded at the packet ingress, like for example, the arrival timestamp, which is required in the precision time control protocol, and as well as for congestion monitoring and other various applications might benefit using this data. And there's also a number of reason codes that are provided by different vendors when the packets are punted. And sometimes these reason codes might give additional information to the applications. And this is another reason why we could probably use this metadata in a better way. And finally, we could also give some more control to the applications by having them insert cookies and have the punted packets come back with those cookies. So our solution to address the above two or the previous two requirements is basically to use the GNetLink model. So SAI provides an capability to receive punt packets or to basically do packet IO using GNetLink, and then more I should say using the user-defined traps. And Linux provides this GNetLink to essentially encapsulate packets from kernel module to the user space or between user space applications. So it's a very generic available Linux capability to send packets from one place to another. So we are going to leverage these two to provide the solution. And the way it works is essentially, let's look at the control plane flow first. Like any application, for example, in this case, P4 runtime application will essentially create a user-defined trap first, and then also create a host interface with a type of GNetLink, and then program the host interface table entry to redirect packets belonging to this user-defined trap to the GNetLink host interface. So the control plane gets programmed here, and we were talking on the programming the host interface table entry. So by default, the packets, any punted packets are programmed to be redirected to the NetDev host interfaces, and this can be changed by this host interface table entry where we can remap them to a specific GNetLink rather than the regular host interface. And once that is done, the ACL entry can be created with the type user trap ID, and then this essentially will program the ASIC to basically take this ACL, and then it associates a metadata to it or a tag identified to it, and then when packets are received on the ASIC matching the ACL parameters, the tag identifier is put onto the packet and then sent, and the kernel module essentially looks at these tags to identify that this is a special type of packet that needs to be processed via the general packet rather than the regular NetDev ports. And it goes to the general, and then there are again tags to identify whether this is to differentiate between the different applications that use the general library. And it goes either to psample, which SFlow uses, or to the generic, the general packet, which is the one that we added now. And then the packet basically is this library module now essentially will pull out the vendor metadata, like all the specifics that we talked about, like the ingress port, the target port, and then encapsulate them and send it to the application side. So the applications can essentially allocate a socket and then do a general connect, and then specify the family and membership ID, and then they will be able to connect to the stream and then receive the packet ends. So this is essentially the data plane flow, and we saw the control plane flow. And let's move on. We talked about the metadata that is being added to the packet, and right now we have these 4 metadata, which is the ingress IF index, the target or the outgoing IF index of the port on which the packet would have egressed out, and then a cookie value to essentially just provide some additional capabilities. We are right now not using it, and the last is the payload data. The metadata is standardized now across the vendors, and it's being used by the P4 runtime application. And I will hand it over to Don to kind of talk about the various enhancements we are doing for the general packet library.
Thanks, Kishan. First, let's turn our attention to the current GE Netlink implementation, and then we will take a peek at what we have planned for the future. Today in PENS, GE Netlink user space functionality is embedded within the P4 runtime service. The usefulness of GE Netlink is not limited to the P4 runtime specifically, nor is it limited to SDN applications generally. We wanted to make this functionality available to other applications that may wish to take advantage of it within the Sonic ecosystem. We made a decision to extract the functions into a separate library and to move the source code into its own repository to make it easier for other applications to consume. After we finished the initial version, we tasked our intern with creating 2 new applications that use the library, a GE Netlink interface sniffer and a packet generator that outputs to GE Netlink interfaces. This accomplished 2 things. We provided these tools to assist with the development and operations in troubleshooting, but also these tools can serve as a user guide to the library itself. As you might guess, our current implementation sends all packets to all listeners, and filtering must be done at the application level. Additionally, packet metadata is fixed, requiring a new manual definition and subsequent implementation from each vendor for each new metadata field. To address these limitations, we've laid out the following roadmap for the evolution of the library. In the next version, we plan to support additional user-defined traps, each of which gets mapped to a different GE Netlink multicast group. Using a single Netlink socket, applications can register for 1 or more punt domains that they wish to listen to. This will simplify filtering without creating any additional socket or netdev complexity. In the third version of the library, we plan to move from our fixed metadata to allowing the user space applications, in our case, P4 runtime, to configure metadata at runtime. For P4 runtime, the GenL packet layer will be reinitialized whenever a new pipeline is pushed. This will provide the new metadata along with some annotations to help the vendor layer with dynamic translations. Now I'll turn it over to Brian, who will discuss packet out.
Thanks, Don. Today, Sonic supports packet outs using the same set of netdevs that are used for packet in. Packets are built by the application and then passed over the socket to the netdev that they want to be used to send the packet on. Packets sent to these netdevs are picked up by the vendor layer, which augments the packets with metadata required for the ASIC to be able to transmit it out the port that's been requested. Let's take a little bit deeper of a look into how this works. When a Sonic application wants to send a packet, it needs to know everything about the packet that's going to be sent. For example, it needs to know the Ethernet header, including the source and dest MAC. It needs to know the IP header, if it's an IP frame, and it needs to know the egress port on which it wants to send a packet. Today, it's pretty easy for most Sonic apps to fill this information in. Topology discovery and management apps like LACP and LLDP need to understand enough of the topology to select the egress port and tend to only build L2 frames. Explicit reply apps like ARP and ICMP tend to build the reply packet from the request and then reply on the same port on which a packet was received. So most of the intelligence living in the application layer is a pretty tractable problem. However, there are some challenges with direct transmit that we'd like to discuss as well. For example, apps that need to broadcast or multicast packets need to generate multiple copies of the packet in the software layer and then send them out to each of the individual net devs. This is inefficient. It's also difficult for apps to provide QoS information that can be used to prioritize control packets on overloaded links. And finally, it can be complicated for performance or troubleshooting apps to determine the right path to follow in modern fabrics. For example, the app layer may select a port, but ASIC state may dictate that packets that look that way would actually go in a different direction. So it can be hard to figure out which way a packet would actually go without understanding the ASIC state and hashing configuration. To address this issue, we've added a new Linux netdev called Submit to Ingress. Applications bind this netdev just like regular Sonic Ethernet ones. And packets that are sent to Submit to Ingress are handled by the switching ASIC. In a sense, the intelligence of building the packet and deciding where it goes can be split between the application and the ASIC. In this case, our application builds the IP packet and then can transmit it without having to get into the Ethernet frame details or picking the egress port. This is similar to the way default gateways work in modern Linux systems and routers. Once the packet's handed over to the ASIC, it looks like just as if it had arrived off of one of the physical ports. And we can leverage the routing table that's already been programmed to the ASIC to decide what happens next. In this example, our IP packet goes through standard routing, WCMP hashing, which picks a next hop group, and then the Ethernet frame gets built using the correct router interface and neighbor addresses, just like any other data plane packet. The ASIC can also apply QoS policies and scheduling to the packet, helping ensure that control packets are prioritized if necessary. Finally, the packet is transmitted out of the port that's been selected by the ASIC. Splitting decision-making across the application and the ASIC allows us to get the packet where it needs to go. This approach provides a separation of concerns and simplifies apps that don't know where a packet needs to go. It enables us to build apps that can be used to monitor performance or troubleshoot traffic by having packets take the same path as data plane packets according to the actual ASIC state. This Submit to Ingress netdev works alongside standard Ethernet netdevs and becomes yet another tool in the arsenal that application developers have to build Sonic apps. Next, I'd like to look at a proposal that we're considering for the next generation of Submit to Ingress. For similar reasons as packet ins, metadata can also be valuable for packet outs. To address this, we can augment the GENL packet driver that was built for packet ins to support packet outs as well. This approach still requires definition, including we need to define a group for how packet outs get sent to the GE Netlink socket. And we also need to define the specific metadata that the vendor layers will have to support. One potential benefit of packet out metadata is it allows us to support Submit to Ingress on multi-ASIC boards or in chassis systems, where we need a different Submit to Ingress for every line card or every ASIC. Packet out loopback can be useful in testing and validation of a switch, and can be enabled with a metadata flag on most ASICs. Metadata can also be used to help classify packets. For example, high priority control packets that need to be sent over data plane, traditional data plane packets. And finally, socket management at the application layer can be greatly simplified if we have one Netlink socket that's used for all packet in and packet out needs. This approach using GENL packet is completely compatible with the Submit to Ingress netdev, as well as the regular Ethernet netdevs used in Sonic today. Applications can pick the approach that works best for their use case and needs. We're already using the submit to ingress netdev in pins today, and it's available for other Sonic apps that want to take advantage of it. The GENL packet approach discussed on this slide is still in early design, and we'd welcome you to contribute your feedback as well as participate in the development of this particular extension. In summary, we've discussed several enhancements that we've built around Sonic packet in and packet out for pins. We're in the process of generalizing these new capabilities so that other Sonic apps can take advantage of them as well. If you'd like to learn more, we have a quite extensive reference design that's been submitted to the Sonic ecosystem. The link's available in the slides. You can also find it under the Sonic high-level designs directory. We also have a reference GENL packet in code that's part of the P4 runtime app today. A link will be part of the slide deck when you receive it. The library code that Don described is currently in development and under review, and we're hoping to make it available as part of Upstream Sonic later this year. If you'd like to get involved with both Packet.io that we've been working on, as well as pins, I'd encourage you to join our mailing list. And if you're interested specifically in Packet.io, we have a sync up meeting every other Wednesday from 2 to 2:30 Pacific, which you're more than welcome to attend. Just send us an email and we'd be happy to add you to the calendar. With that, let's wrap up and we'd be happy to take any questions.
Thank you for this great talk. It was very interesting to see getting the switch devices being closer integrated into Linux. I think that's a very exciting development. I have a few questions, and maybe let's start with the more specific ones. I think this Gen netlink design looks really interesting. Are there any performance considerations if you compare the new Gen netlink approach to the existing one? Do you expect any differences or improvements?
I can take that. I think on a quick note, we haven't seen any noticeable performance degradation or anything because the path is almost similar in the sense that the vendor module receives the packet, looks at the metadata, and then either puts it on the netdev or puts it on the GENL, and it's a socket interface. So we have not had any major issues, and we have not done a head-to-head comparison, but I believe we have not seen anything obvious. But one thing that we had some issues is basically providing the allocation buffers for the receive path. So we had to tune that a little bit to handle traffic at a higher rate. I think, Don, you wanted to add something?
Well, I was going to say, I don't think we're really expecting any real high volume flows to go through the GNet. Like, I mean, maybe in the future there might be some, but really it's more the one-offs that you expect, one-off packet type stuff that you expect that way.
Okay, so you wouldn't even the performance it's not a concern in the design because that's not what the whole system is designed for in this specific case.
No, but I mean, as soon as we say that the next application to use it will be streaming stuff. So we will address it if and when we need to. But
yeah, I think that I mean, for line rate apps, typically we're seeing things like DPDK where user space apps want to directly bind and dedicate CPU resources to receiving packets. Most vendors support something like that in their SDKs. That's not something we've seen generally supported in Sonic. So either of these approaches is typically still going through the kernel. Technically, vendors could implement this part in user space, but there's still several context switches that are going to happen. So you can probably, I mean, I don't want to make any performance claims, but it's not just one-off packets, right? There's going to be large amounts of packets per second, but it would be similar to what you'd expect through your standard kernel interfaces. The one other thing that I can mention about this approach is, as Kishan mentioned, we wind up broadcasting packets to netdevs today, and we use kernel filtering or application level filtering to filter out unnecessary traffic. So in environments where you do have a lot of apps that are requesting traffic, the GE Netlink approach, specifically the roadmap approach that Don discussed, allows us to have the ASIC and specifically the ACLs do some of that filtering on our behalf. So we're only sending copies of packets to the apps that require them, and apps don't necessarily have to worry about eliminating or filtering out traffic that it doesn't need because it just won't see those packets.
Yeah, that makes sense. Yeah, I'm really interested to see how this works out and maybe trying it myself sometime. Just a quick question from my understanding, the GenLink socket that you talked about, I've never used that specific subsystem before. So what kind of socket is it? Can I imagine it like a raw socket, or can you maybe give a brief introduction on what to expect as a user from this kind of interface or socket?
Yeah, it's similar to a raw socket, but when the packets, the format of the packet is much more complicated over there rather than the regular, for example, the socket where the NetDev packets come. But fortunately, Linux provides multiple libraries, like there is a libnl netlink library that is available, and it abstracts out all the complexities out for the user. So you just have to initialize, connect. So there are APIs to connect to the multicast family, and when the packet is received, you can essentially define these netlink attributes, and then it will decode the packets and then put them into different placeholders for you. And then it's pretty straightforward to then parse the packet and pull out the information. Yeah, this is the example of the packet format. Again, what is shown here is a much more simplified version of the header. But along with the different, like the first part, which is the GE Netlink headers, has more information about the Netlink family and the multicast ID and things like that. So the library provides APIs to abstract out all this these information.
But it is pretty straightforward to implement. And when the source becomes available for both the library and the two applications we've written, you'd be able to follow that example. That it's really straightforward.
Okay, sounds great. I mean, yeah, that's
regular network programming.
Yeah, the first thoughts is basically how difficult is it to use, but yeah, it's really straightforward. Cool. I'm really looking forward to trying it. Might I ask, you just said you plan to share it or put it on the internet, basically. When do you expect this to happen?
It's kind of contingent on the Azure approval process, basically.
Okay.
So we've submitted the high-level design. Once that's approved, then we'll move to the next stage at getting the code approved. But I mean, hopefully not too much longer.
Yeah, just in sort of what's available now, submit to ingress is part of the image, and that's something that we're using in pins. The receive GE Netlink stuff is also part of the open source and upstreamed P4RT app. So users can already get a preview of this if they want to take a look at the engineering details. The parts that we're still in review on are the library, so allowing apps to more easily bind a socket and avoid even the complexity of GNL and binding that, as well as some of the packet out metadata work that we introduced as a proposal. So we're going through, as Don mentioned, the standard Sonic review process, and obviously through that, there's feedback we get. We use that to enhance the project, and then we're currently targeting the December or November release of this year for both of these.
Okay, sounds great. Yeah, thank you. It was very interesting talk, and I'm really looking forward to trying it out, or maybe using a Sonic image that includes all these features. Thank you.